In this video, we're going to take a look at doing a visual trace of the insertion sort algorithm to give you a better feel for the intuition behind how it works. All right, so I have here my sample input. This is going to be kind of similar to what we had when we talked about selection sort. So here I have a random input. And so I want you to think for 1 second, how will this shuffle around on the screen as we simulate the run of this insertion sort algorithm? How should it look? And here we go. So we have the dark side, right, which is basically everything that is sorted. So notice basically that we're growing it, right? So it's like we go to the the element right to the just to the right of that region, pick it, and push it to the left until it goes where it's supposed to be, right? So sometimes it has to travel a fair distance, right? Sometimes it has to travel super far, and then sometimes not so far. Okay, let's actually take another look at that. So again, right, some elements have to go super far, some of them don't, right? So if I have something that's really large, it can basically just stay where it's at. If I have something super small, it needs to go all the way to the other end, right? So I do that again and again and again, right? And eventually, right, I get my sorted output. So not bad, not bad. In general, right, when we have a random input, everything is going to kind of act kind of normal. So this is not too surprising. So yeah. All right. Moving forward, reversed input. Reversed input. Maybe think to yourself, how will this look? It'll look terrible, actually. So basically, every time we have a element and we're trying to insert it into our sorted region, we're going to have to go all the way to the far side of it, right? So this is actually the worst case. So notice every time, new element, all the way in, all the way in, all the way in, again and again and again and again. So this is basically our worst case. So this is this is one thing where we definitely do not want insertion sort to run. This is going to be our worst case for this algorithm. So hopefully, though, maybe there's something else we can look at, right? That maybe will give us a better runtime. All right, I'm out of things to say, and I still got like 2 more elements. So I got like another second to kill, and then I'm done. Okay, so let's take a look at the next one. Yeah, partially stored input. How will this look? Take a look. Now that's nice. Okay, if you look at that, right, that should instantly seem to do that's very nice, right? We'll do that again, right? So instead of me having to running out of stuff to say, right, this is like I can barely get through a sentence. It just instantly picks up everything. Because notice, right, insertion sort, right, is going to basically go, it's told to sort an element, so it starts moving to the left. Well, if something's nearly sorted, then the place it belongs is going to be pretty close to it. So most of the things in that collection, right, that array, will only be moved by a couple of indices, right? Instead of having to be moved, all the way to the end, like with the other example, they get moved just to their neighbors, right? That's super simple, super fast. And this, right, is the ideal case here for insertion sort, right? So best case, right, is a nearly sorted array. If we throw a nearly sorted array at insertion sort, it'll be, well, in algorithm analysis terms, it'll end up looking like an O of n algorithm instead of an O of n squared algorithm. So very, very nice. All right, so that's some intuition for you guys. Hopefully those algorithms make a little bit more sense now.